Right now, as you watch this, roughly 3/4 of Earth's ocean floor is completely invisible to science. We have sharper maps of Mars, the Moon, even Venus, than we do of the seabed beneath our own waves. But a coalition of over 185 organizations across dozens of nations is sprinting to change that before the decade ends. And what they're finding down there is rewriting what we thought we knew about our planet. This is the story of Seabed 2030. Let's start with a number that should shock you: 27.3%. That's the portion of the entire global ocean floor that has been mapped to modern bathymetric standards as of the most recent data update in mid-2025. 27%. The other nearly 73%. It's essentially blank space on our charts. Terra incognita, except it's underwater. And here's why that's not just a trivia fact. That unmapped seabed isn't some barren desert. It contains mountain ranges taller than the Alps, canyon systems that dwarf the Grand Canyon, and ecosystems so rich they harbor species that don't exist anywhere else on Earth. But because we can't see them, we can't protect them, we can't navigate around them safely, and we can't plan for the natural hazards they create. Think about tsunami early warning systems. When an undersea earthquake triggers a massive wave, the shape of the ocean floor directly determines how that wave travels, where it intensifies, and which coastlines get hit hardest. If we don't know the precise contours of the seabed, our tsunami models are working with enormous blind spots. The same applies to undersea cable routing, the fiber optic lines that carry over 95% of intercontinental internet traffic. Those cables sit on the ocean floor, and laying them through unmapped terrain is like building a highway through a landscape you've never surveyed. Climate science depends on this data too. Ocean currents are shaped by the topography beneath them, and those currents regulate global temperature, distribute nutrients, and influence weather systems that affect billions of people. Without a complete picture of what the seafloor looks like, our climate models are permanently incomplete. So who's tackling this? The main effort is called the Nippon Foundation GEBCO Seabed 2030 project, and it launched in 2017 at the United Nations Ocean Conference. It says GEBCO, the General Bathymetric Chart of the Oceans, is a joint program of the International Hydrographic Organization and the Intergovernmental Oceanographic Commission of UNESCO. They're the only body on Earth with an official mandate to map the entire ocean floor. The Nippon Foundation, a major Japanese philanthropic organization, provides core funding and strategic vision. When the project kicked off in 2017, only about 6% of the ocean had been mapped at useful resolution. In less than 8 years, that figure has climbed to 27.3%, which means the project has added the equivalent of over 94 million square kilometers of bathymetric data through global partnerships and technological advancement. In just the most recent annual cycle alone, they added over 4 million square kilometers of newly mapped seafloor, an area roughly the size of the entire Indian subcontinent. Seabed 2030 operates through 5 regional data centers around the world. There's the Southern Ocean Center at the Alfred Wegener Institute in Germany, the Atlantic and Indian Ocean Center at Columbia University's Lamont Doherty Earth Observatory in the United States, the Arctic and North Pacific Center jointly hosted by the University of New Hampshire and Stockholm University, the South and West Pacific Center at New Zealand's National Institute of Water and Atmospheric Research, and a global data center at the British Oceanographic Data Center in Liverpool. All the data these centers compile feeds into a freely available map called the GEBCO Grid, open access, free for anyone to use. So how do you map something 4 kilometers underwater in pitch darkness? The primary tool is multi-beam sonar, specifically multi-beam echo sounder systems. These devices are mounted on a ship's hull and work by firing a fan-shaped array of sound pulses straight down toward the seabed. When those pulses hit the bottom, they bounce back, and the system measures the return time of each individual beam. Because sound travels at a known speed through water, adjusted for temperature, salinity, and pressure, the system can calculate precise depths across a wide swath beneath the vessel. Modern systems can fire hundreds of individual beams in a single ping, generating up to 864 depth soundings at once across a swath that can span 2 to 5 times the water depth. As the ship moves forward, these swaths stitch together into continuous strips. Hydrographers call this process mowing the lawn, sailing back and forth in parallel lines to build a complete picture of the bottom. The result is a detailed three-dimensional digital elevation model of the seafloor, color-coded by depth, revealing every ridge, trench, and seamount in the survey area. But there's a catch. The deeper the water, the wider each sonar swath becomes, but also the lower the resolution. And the ocean is enormous. Even at cruising speed, a single survey vessel can only cover so much ground. That's why crowdsourced bathymetry has become critical to the Seabed 2030 mission. Fishing boats, cargo ships, cruise liners, and even private yachts are being recruited to collect depth data using their standard navigation instruments while they transit between ports. It's not as precise as dedicated survey-grade multibeam, but it fills gaps that might otherwise take decades to reach with research vessels alone. There's also satellite altimetry, which works from orbit. Satellites measure tiny variations in the height of the ocean surface caused by gravity anomalies beneath. A seamount with extra mass creates a slight bump on the surface. A deep trench pulls the water level down fractionally. This technique gives a rough outline of major features, but the resolution is nowhere near what sonar provides. It's more like a blurry sketch that tells scientists where to look more closely, and when scientists do look more closely, the discoveries are extraordinary. Take the Blake Plateau off the southeastern coast of the United States. For decades, researchers assumed this broad, odd and flat stretch of seafloor between roughly Miami and Charleston was mostly barren sediment. Then, Noe Ocean Exploration, working with a coalition of government agencies, universities, and private partners, launched a multi-year campaign to systematically map the region using 31 overlapping multi-beam sonar surveys. What they found was staggering. The largest known deep-sea coral reef ecosystem on the planet, the province of coldwater coral mounds, stretches 500 kilometers long and up to 110 kilometers wide, covering 6.4 million acres, an area larger than the state of Vermont. Their automated analysis identified 83,908 individual coral mound peaks in the data. A section nicknamed Million Mounds by scientists contained the densest concentration of coldwater coral structures ever documented anywhere. These aren't the tropical reefs you see on nature documentaries. Coldwater corals like Desmophyllum pertusum grow in complete darkness at depths between 200 and 1,000 meters, in water averaging just 4 degrees Celsius. They don't rely on sunlight at all. They filter nutrients from deep ocean currents, in this case the massive Gulf Stream flowing right past them. Some individual colonies are estimated to be over 4,000 years old, and until the mapping was completed, nobody knew the full extent of what was hiding right off the American East Coast. Then there are the seamount discoveries. In early 2024, the Schmidt Ocean Institute's research vessel, Falkor 2, was on a routine transit from Costa Rica to Chile when its multi-beam system flagged gravity anomalies beneath the surface. As such, the crew diverted to investigate and discovered 4 entirely new seamounts, underwater mountains that weren't recorded in any existing bathymetric database. The largest stands 2,681 meters tall, covers 450 square kilometers, and sits just 1,150 meters below the surface. To put that in context, that's a mountain nearly 9 times the height of the Eiffel Tower, hiding beneath open ocean that ships had been sailing over for centuries. But it didn't stop there. Over the course of 2024, Schmidt Ocean Institute expeditions explored roughly 25 seamounts along the Nazca and Salas y Gomez ridges off Chile, a 2,900 kilometer underwater mountain chain stretching to Easter Island. They found thriving ecosystems on virtually every peak: deep-sea coral gardens, glass sponge fields, squat lobsters, rockfish, king crabs, and brittle stars. Scientists identified over 150 species suspected to be entirely new to science. They even filmed a live Promicoteuthis squid, a genus so rare that only 3 species had been described from a handful of specimens, some collected in the late 1800s. Every single one of these discoveries was made possible by mapping. No mapping, no knowledge. No knowledge, no protection. Now here's where it gets complicated. One of the biggest obstacles to completing the global ocean map isn't technology. It's data sharing. Governments, militaries, and private companies hold enormous bathymetric data sets that have never been released. National hydrographic offices in many countries have detailed surveys of their coastal waters, but consider them sensitive for defense or economic reasons. The offshore oil and gas industry has mapped vast tracts of seabed for pipeline and drilling operations, but often treats that data as proprietary. And naval forces around the world have some of the most comprehensive seafloor surveys in existence. collected for submarine warfare and navigation, but sharing them would compromise operational security. Seabed 2030 has been working to bridge these gaps through diplomacy. In the most recent reporting period, 14 new organizations contributed data for the first time, including contributions from 5 countries that had never participated before: Comoros, the Cook Islands, Kenya, Mozambique, and Tanzania. The total network now includes over 185 contributing organizations worldwide. But getting the remaining 73% mapped in the next 4 years will require an unprecedented acceleration. More ships collecting data, more governments opening their archives, more private companies donating survey results, and more investment in autonomous underwater vehicles and uncrewed surface vessels that can map remote areas without human crews. The project has also become a flagship program of the United Nations Decade of Ocean Science for Sustainable Development, lending it political visibility and encouraging member states to participate. At the 2025 UN Ocean Conference in Nice, the global community endorsed accelerated ocean mapping as a priority for climate resilience, biodiversity conservation, and sustainable development. So why should you care about the shape of the ground beneath an ocean you may never visit? Because it affects almost everything that touches your daily life. The seafloor determines where fish populations concentrate, shaping food supply chains. It dictates the paths of the cables that carry your emails, video calls, and streaming services. It governs how tsunamis, storm surges, and undersea landslides behave. It conceals mineral deposits that may fuel the next generation of technology, and it harbors ecosystems so ancient and biodiverse that losing them before we even discover them would be one of the great tragedies of our era. We are living through the final chapter of geographic discovery on Earth. When Seabed 2030 finishes, whether on schedule or a few years late, it will mark the first time in human history that we have a complete map of our own planet's surface. Think about that. Every continent, every island, onto every mountaintop was charted centuries ago, but the ocean floor on the majority of Earth's actual surface remained a mystery until this generation decided to look. If you want to follow the progress, the GEBCO grid is updated annually and available for free at seabed2030.org. And if you found this fascinating, let me know in the comments what part of the deep ocean you'd want explored next. And don't forget to subscribe so you catch the next deep dive.